Okay, so this is going to be basically last lecture in the C++ series. And okay, let me add notes file. Okay, so we will cover basically how to deal with HTTP stuff, request, responses. Okay, we will see how to deal with SQL stuff. We will use PostgreSQL and see some very basic stuff about how to connect to database in some sort of queries, updating data, inserting data, getting the data back, that sort of stuff. And the biggest topic is going to be threads in C++. So we will do this HTTP and SQL part first, and then go to threads, because threads on their own will not be very useful except in some very specific circumstances. But if you are dealing with network stuff and databases, there will be way more use cases where you want to keep things on separate threads. So while one part of code is waiting for something to complete, you are dealing with some other part of your code in parallel. So thereby reducing the total waiting time where your code is basically doing nothing and only waiting for something to complete. So for HTTP, again, we will use a library, okay? And there is a very famous library called, uh, it is called libcurl, and this is the library behind curl utility. So that project is basically a library first, and then curl utility is written on top of the library as a standalone utility, as well as some sort of uh, way to expose a lot of functionalities within the library that you can use without involving the library itself. Okay, and this library is mostly around C APIs. It has basically C API. We do not really want to use C API here. Technically, we can. Nothing extremely bad will happen. Just that we will not be able to use C++ goodies with that API, because that particular library has no idea about any of the goodies which are present in C++, but not in C. So there are two ways. One, we can wrap this library which exposes only C API and wrap it in a way so that it is usable while using stuff from C++, or we can use some other wrapper library for this, which is exposing it as a C++ library using C++ goodies. Okay, so for our use case, we are going to use wrapper, and that wrapper is called, oh wait, what is it called? I forgot the name. Okay, yeah, it is called, oh shit, it is called curlpp. Okay, so this is basically a wrapper which wraps libcurl and turns this graph ton of C APIs into a bunch of C++ objects and their member functions. So instead of dealing with raw C API, we deal with C++ counterpart, and obviously we get to use a lot of goodies of modern C++ with that. So, okay, this is how it basically works. So we include these bunch of headers from that curl++ library. And then we can forget this post request part here. Wait, let me comment this whole thing out. Okay, and to get started, what I want to do, I want to pull some data, as in I want to send some very simple GET request and capture the response. Okay, so there are two variables that I need to define. One is request that I am using everywhere here that you can see, and one is called this cleanup. And if you pay attention, this cleanup is not being used anywhere at all. Okay, as listed explicitly. The point of this is that we declare it within this smaller scope, and as soon as this part is done, this goes out of scope, and since it is going out of scope, its destructor will be called, and from within that destructor, we can perform cleanups that is required by curl library behind the curtain. So if instead of using this particular wrapper, we are using curl library directly. So before we can send any request, we have to do some manual initialization of the library, and then we do whatever stuff we want to do, and then we have to call a bunch of functions to perform the necessary cleanup that so that it basically uh, removes and unwinds everything that it has done at time of initialization. In C++, we have constructors and destructors, so possibly we can deal with that initialization and deinitialization part using constructor and destructor. So that is exactly what it is happening here. So cleanup part is handled here, and it has no other use, so it is not used explicitly, just that it is here so that once this part is done, the destructor is called and that library related cleanup is done properly. Okay. Now we have this request object, and then here we can uh, set bunch of options, and these options can be like I can specify URL that I have to specify anyway. Okay, I can specify which HTTP verb it is going to be. Is it get? It is post? It is put? It is delete? It is patch? It is something else. Okay, I can specify some body to which will go with the request. I can specify a bunch of headers that I want to pass along with the request. Okay. Similarly, there are some other options which I can specify. For example, at times I may want it to perform the redirection on its own. Okay. On other times, I may want to deal with that redirection part at my own end. Okay. So all those things are configurable. So for example, at the very simplest case, we will do only this part, create this request object, and then I set the option and specify that I am setting this URL option, and then I specify HTTP google.com. In case you notice, there is no www part here and there is no HTTPS here. Okay, and then I do this request dot perform, and now I want to build it. Okay, so I want to run this part, and then okay, now if you see the response, I am getting an HTML response that is expected, but it says that the document has moved and it is giving me basically that 301 response code. The response code is not printed here because that is not really part of body. So that I know here that it moved to somewhere else and the target URL is somewhere else. So for example, here it says that it is redirected to this www.google.com. So if I am going to handle this manually, I will have to get the response code and get the destination URL and then make another request to that new URL. Or if there is no specific requirement for me to handle this particular case in any special way, as in if it is going to be a simple redirection, what I can do, I can say that, hey, do that redirection for me. Okay. So here I set another option and it says follow location to true. So when this request goes, the response comes, the library sees that it is HTTP 301, that is a redirect, and it will find the destination URL after redirection, and then it will send another request to that new URL and give me body of that request. So if I set this to true, build again. Okay, now if you see here, we are not seeing any 301 moved or some other stuff. We are seeing some, again, HTML document here. There is some sort of a script, bunch of stuff, and then it basically completes. So basically, this is the stuff that your browser is getting when you are sending this to this request to this google.com. Okay, so this is how a very simple HTTP request works. Now, obviously, there can be possibility that something goes wrong. So for that, we have a bunch of exceptions uh, that we can handle here. Okay, so this is how a very simple GET request is going to work. Now, I want to send some data. Okay, as in I want to make a HTTP post request, because most of the time you will be using post request instead of simple get ones, because you need to push some data, you need to maybe push some sort of query or some other stuff, or maybe you are trying to upload something, whatever. Okay, so what I can do here, I can specify the data. Okay, that this is the data that I want to specify in the post request. Then I can have a function to do this post request for me. Okay, I specify the URL, I specify the data, and then here in this particular function, I am taking URL and data, and just like previous case, my cleanup and request, because I want that cleanup to happen once this function is done. URL I am already getting, so just like previous case, I set the URL. Okay, and now here, since I am making a post request, at times I will also have to set a bunch of headers properly. For example, if I am sending a JSON body, right? So I will have to set content type properly. Otherwise, there will be servers which will not really process this properly, and they will be mostly correct in doing so, because I have not specified the content type properly. So I can specify content type here, and just like this, I can also specify a bunch of different headers as well. Okay, so whatever headers I want to specify, I create a basically list. Okay, and I can add as many headers as I want in that particular list. Okay, I can have only one header, I can have 10 headers, I can have 5 headers, depends. And then I set another option called HTTP header, and then I specify this entire list that, okay, these are the headers that I want to be sent with this particular request. Then for post fields, I specify that post data. Okay, and then I also have to specify the data size. So for post field size, I specify this data length here. Okay, and then I need to get the response. Now in the previous case, if you note here, I did not specify any explicit location where I want the output. Okay, I did not ask it to write the output in some sort of variable and then printed it, or to dump it in some sort of file. I just said that, okay, make this request. And by default, it dumped entire response directly on the console. There will be cases where I don't want this to happen. I want this in some sort of variable, or I want it to go into some sort of file, or possibly in some sort of database, or to some other part of code. So for that, what I can do, I can have a stream where I can take the response, and then I can specify yet another option called write stream, and then I give my variable. Okay, so here what I am saying that, hey, I have this is basically a stream object. Okay, and whenever you have something to write after the request as an output, use this particular stream to write. Okay, now this particular library doesn't really care about which type of stream we are using here. It may be a simple string stream, as in this will be entirely in memory, looking like a string. It may be a file stream. It may be some other type of a stream or some stuff that you have defined on your own, and you are inheriting from a generic stream object in C++. Okay, so as long as it is uh, like a generic stream, specifics don't really matter for this library, and this will basically work properly. So instead of doing this, what you can do in case you want it to land it in some sort of file, you can specify a file stream here, or if you want it to be sent to somewhere else, you can possibly turn that into some sort of a stream and then send it there, or you can take it in memory and then in next step you can send it somewhere else. Okay, so we set all these options and then we do just this my request dot perform, just like previous case. Okay, and then once this is done, we know that whatever response we got, this is part of this string stream. So from that stream we get the string, we return it, and then we basically print it. So if I build and run it, yes. Okay, so this is the response we are getting from this particular service. In case you don't know, this is a very generic service where you can send bunch of requests and get bunch of boilerplate responses just to test your HTTP client stuff. Now, if you note here, we did not have HTTPS, only HTTP. Here we have HTTPS, and for this HTTPS part, we didn't really have to do anything special apart from specifying this nifty little S here, and rest of the stuff is automatically handled by this curl library on its own. Okay, so this is the basics of how we can do that, and for rest of the stuff, it's going to be very similar. Basically, most of the time you will be doing get and post, and when you are not doing get and post, you are doing say something like put request or delete request. You will basically set a bunch of options for your request, and rest of the stuff will remain largely as is. Okay, so most of the time you will be setting some sort of headers. For example, if you are specifying some sort of authentication, there is JWT token, it will go in the header. There is bearer token, it will again go in the header. Okay, and body will mostly go like that, and you can specify the content type, and in response you will most of the time get either JSON or XML or some other structure format, and then you can use a suitable library to parse that output and extract some data out of that. Okay, any questions so far? Anyone got any questions? Okay, I suppose there are no questions. Now, there is one more thing that we can cover with this. If you remember from initial lectures, I think it was in lecture 1 itself, probably, we talked a little bit about CMake, and I mentioned in a passing remark that these things can also find libraries in your system and find the suitable paths and flags that you need to specify to compiler. So instead of doing all that stuff manually, you can let the build system handle all that nitty-gritty stuff there. Okay, so for this curl plus plus thing in CMake, I did exactly that. So you have at least some sort of template to use for your future projects. So here what I am doing, if you remember in previous cases, CMake file was looking something like this. We were basically adding line after line specifying which executable to build from which set of source files. Here we are doing little bit extra. And what we are doing basically two things. One, we are trying to find that curl plus plus library. Okay. And we are trying to find how to link with it without having to specify the flags manually. And we also are going to do the same thing for two separate platforms in one shot. Okay, so on Mac OS, the paths are going to be different. On Linux, the paths are going to be different. On Windows, it is going to be something different. And obviously, for different platforms, I do not want to write completely separate CMake list because CMake can deal with those differences to a reasonably good extent. So we are going to use that thing to work on both platforms. So here what I am doing, I am just checking for the OS. If it is Darwin, I set this Mac OS variable to true. And if it is Mac OS, I set yet another variable because on Mac OS there is another package manager called Homebrew. So that will install in its own path if I install something via Homebrew. And then I include some modules from CMake, okay, and then I ask it that, hey, I want this particular library named curl pp. It is required, and if it is required, I want the variables to start with this particular string, okay. And then I basically print these variables that, okay, what are the include directories, what are the linking flags that are coming with this particular library. So I don't have to specify this or this manually. CMake will basically figure it out. And then I am basically saying that if it is macOS, I want both of these to be specified in list of include directories. And then for this curl pp project, I say that target link library for this particular binary, link curl pp using whatever linker flags were made available to you. Okay, so again, here I don't really care what are the flags. Am I supposed to specify -l curl pp -l curl or some other weird combination? Do I have to specify OpenSSL or some other stuff? I don't really care. I don't care about any of that. Okay, I don't have to think what are the transitive dependencies that I may have to link separately with this. I don't really care about any of that. All that stuff will be taken care of by CMake itself. So I specify only this part basically that, hey, I want this particular library, find it, and then set some variables. And then based on those variables, I specify them either for include directories or I can specify them for linking or possibly both. Okay, and that is how it basically works. And if I do this, the same CMake file is going to find curl++ on my macOS device as well as my Linux device on both cases. So this is one of the biggest reasons why these build systems are being used, apart from speeding up builds and building only the part of code that actually changed. This is yet another pretty huge reason why you may want to use a proper build system instead of having a set of scattered files and some sort of ad hoc build scripts, because then you won't be able to find these libraries on your own. You will have to write a lot of code. Why bother doing that if CMake or something like CMake is already going to do it anyway? Okay, so this is where basically HTTP part mostly ends, because there is nothing too much about this. Okay, most of the stuff is going to be done like that, and for more extensive use cases, I will share links of documentation from this library as well as underlying libcurl library both. So if there is something that is extra that you want to do, you can possibly look into the documentation, find the example codes. At least libcurl comes with a lot of example programs, and then you can utilize that. Okay. Now for this, okay. Then we come to database. Give me a minute. Now, just like HTTP, we are going to use some sort of library, and the only difference is many times different databases can have their own dedicated libraries, or one can find some sort of meta library which can talk to wide array of DB engines. Okay, so for example, we can use some library to talk to MySQL or MariaDB, or we can use some library for PostgreSQL, or possibly some other database, including uh, and for some other database, it can be either relational database or it can be non-relational one like MongoDB, or it can be some sort of key value store type of thing, or some sort of some other rather modern database which is either provided by some cloud thing or doing some other stuff. The point is that most of these are going to have some sort of library which you can use, and then there can also be libraries which can provide you access to multiple databases in one shot. So you can pick some library for that and be done with that. Now, for our use case, we are going to use PostgreSQL. Okay, and for that we are going to use, again, there is a library called libpq. Okay, and this is again exposing only C API. And since we do not want to use C API directly, we will use its C++ wrapper. And this is basically C++ wrapper on libpq. Okay. So we are going to use this PQXX, and we will basically deal with bunch of things. And by bunch of things, I mean connecting to database, running some SQL query, and reading data from output of some SQL query. For example, select query. Okay. Okay. Now for that, we include some sort of header here. Okay. And then we specify something called a connection string. So database connection works like this. Okay, so we have this, and then we specify something called connection string. Okay, different database engines can have slightly different format of connection strings. So generally, we have to specify these in connection strings. Okay, we have to specify database, it is called db name, and we have to specify user, is user, then we specify password, it is password, Then we have to specify host. It is host ADDR. Then we have to specify port. Okay. So the format is like, okay, wait. This is parameter and this is name. Okay. So to make the connection string, we basically use name equal to value and then wait, name 1 equal to value 1, name 2 equal to value 2, so on and so forth. Okay. Now here, if you see, I have specified database name as test database, user as my own username, password as my own password. This is the host address, that is my local host IP, and this is basically it is the default port. Okay. So I specify the connection string and then it will try to connect to this particular IP and port and try to authenticate with given ID and password, and then it will try to connect to the database. So if any of the parameters are wrong, the connection will not properly work. Okay, even if you misspell this database name, it will again not really work. Okay, so this has to be proper, and then we can check for this whether the connection is open or not. Okay, so right now I am only going to do this much, and I will wait. It is lecture 8. So here it says that open database successfully, which means my connection string is actually working. So now I can remove this return 0 and then I can do something else. Now I want to execute some query. Okay, so what I need a worker object, create pqxs work object for connection. Oh wait, what? Execute SQL query commit. So we specify some sort of SQL statement that's going to be a string, and then uh, we create the worker object dot execute SQL and then commit. Now, if you pay attention here, you will see that this is wrapped inside this curly braces to create a smaller scope here. And the reason is that the underlying library does not really want to use basically reuse the worker objects. Okay, so the idea is that you open a connection, you reuse the connection. Okay, you don't have to drop the connection and reconnect, then drop again, then reconnect. Don't do that. You connect to database, get the connection object, and then you keep reusing the connection object as long as it is required. Okay, for workers, this is basically use and throw stuff. You create a worker, execute something, you throw the worker out. Okay, so if we don't reduce the scope of this thing, we will have to create multiple worker objects, which will basically become invalidated after this dot commit is called and this SQL statement is done with, and then we will basically end up accidentally using an invalidated object, which will basically throw error at runtime. So to avoid all that hassle, we just wrap it inside inner scope. Okay, so wait, let me wait. We can do return 0 here. Okay, and now I can build it here again. Okay, so here I am running that create table query, so it should create a table. Let me open a shell here. Okay, give me a minute. Hmm. Okay, how did I connect to it? So I connect to the same database. I see there are no tables created. Okay, so now I run this. Open database successfully. I come to here again. I run this /dt again. Okay, the company table is created. Okay, so this is a very simple SQL query. Similarly, we can insert something. Okay, we can run an insert query, and just like previous case, we create a worker, execute SQL, and then we do commit. And then I can return 0 from here. Okay, what I can do here, drop table company, otherwise it will throw error at runtime. Okay, this is done. Okay, table is created again, and then I can run select star from company. Okay, and the records are inserted here. Now I want something extra, and what I also want to select some records, and then I want to go through that. So wait, let me drop the table again. Okay. Now for select queries, it is slightly different. Select query, use non-transactional worker, and then execute SQL, get result in PQXX result object, then iterate over result object. Okay. So here I create a non-transactional worker. Okay, this one is called actually transactional worker. Okay, so I run this query just like previous case, except I am not doing the dot commit. Okay, so I run this query and then I take the result in this result object. I'm just initializing it using the return value from this exec function here. And then I basically create an iterator and iterate over this result object. And then I can simply access all of that. So it will basically uh, look like this. So here I am iterating here, okay. And then each iterator will give me basically set of columns. Okay, so here I specified select star. So I will get 1, 2, 3, 4, 5. I will get total 5 columns. Okay, and they will come basically in the same order here. So it is the same order which was specified here, and if I am not specifying any other order, it will come in the same order. If I specify some other order here, these index will have to be updated accordingly. So here the first column is ID, so 0 index will be ID, second then it is name, so 1 will be name, so on and so forth, all the way till last column, which is index 4 here. Okay, and then we can specify the format in which we want the data, where we want it as a string, as boolean, as integer, as some sort of floating point value. Okay, So this is how we basically do the stuff, and once we are done, we can basically close the connection using dot close. If there are exceptions, we can either print it or try to deal with them using some more specialized exceptions classes. So basically, this is how we mostly deal with databases. There is one more topic that is not present here, and that is called basically prepared queries. And the idea is that suppose I want to insert some data or update some data, okay? And I need to specify these values. There is one way I can just append the strings, but that will create SQL injection. So I can't really do that. So for that, we will have to use something called prepared query. So preparing SQL query using variables. Do not append them as a string. Creates SQL injection. Use prepared query. Specify values of parameters in prepared query at time of execution. This results in no more SQL injections. Okay. So we covered this very basic part, and then for that this prepared query stuff, I will send you the documentation. Okay, it is very similar to this, just that at time of specifying this exec, you also specify a bunch of other variables which are going to pass values in the prepared SQL query, which instead of values has bunch of placeholders. Okay, any questions so far?
I don't see any questions on chat.
Okay, fair enough. Okay, now for this PQXS thing, there is one more part in CMake, and that is that instead of specifying everything in one location, you can break it into bunch of different sub projects, and each sub project can have its own uh, CMake file, and you can include those entire projects in some bigger project. So for that, I turn this database part as its own project with this teeny tiny small CMake list file. And then what I have done, I have basically added this smaller project in the bigger one by using add subdirectory. So this is yet another common thing that you may need from time to time, especially if you are breaking your bigger project into a bunch of smaller projects, which you should be doing anyway if the project is getting more and more complex. So at that stage, you can have separate CMake files, and then you can use add subdirectory. So this is how you do it. And just like this, here we are creating an executable. You can also create a library, and then you can link that library with something else in some other part of code. Okay, now we are basically coming to threads part. So, okay, you want this code. So what I will do, okay, I will this file, and then I will basically comment out this whole thing. Okay, and then we will do this thread part here itself. Okay, so okay, let me have a placeholder int main return 0. Back to lecture 7. Okay, fine. Okay, now we come to next topic is threads. Okay, so threads are basically part of within a process. Okay, so a process can have multiple threads. It will have at least one thread. Okay, a thread cannot really have multiple processes. So use cases do something else while some part of code is waiting for something external. Maybe you are writing to file, you are waiting for it to complete, you are trying to connect to some service, you are waiting for it to connect, you are hitting some sort of query to database, you are waiting for the database to respond or send some data, or you are downloading something, you are waiting for that to finish, whatever. Okay, or maybe you are waiting for the user to do something. Does not really matter. If there is something else which can be done in parallel, might as well do that in parallel. Second is performance. Again, this is something not guaranteed. Code has to be specifically structured in a way that allows performance to happen. Okay, then there are caveats. If we are not careful, we end up basically performance penalty, as in something was taking 1 minute before we introduced threads, and we have introduced threads, and now whole thing has gone to gutter, and then it is taking 10 minutes. That happens. Okay, it can have locks, it can have data corruption, it can have race conditions, etc., etc. So on one hand, it gives us a lot of flexibility and the scope of a lot of performance improvement, and on other hand, it also basically unveils a lot of basically foot guns. Okay, and these foot guns are not really something specific to C++. These are going to happen in basically any language that allows threads to happen. Okay, for example, if you do it in Golang, you can have performance penalty, you can have deadlocks, you can have race conditions, data corruptions, anything. You can do this in Java, same thing in C Sharp. The only case of exception will be probably Python, but that is because that the threads are not really true threads, as in no two threads are going to run at same time because of global interpreter lock. So in that case, you don't get this data corruption, race condition, that sort of stuff, but then you also do not get absolutely any performance improvement at all. So this is not really specific to C++. Okay, so if you basically learn how to deal with these things, you can use the same concepts pretty much anywhere, irrespective of a language or stack that you are going to use. So let us start from something very basic. Okay, for threads, we will include another header. called thread, and then we will create a function, and we can basically print something. This is fun. Okay. And then we can create a thread. We want to create a thread, and we can, it is as simple as declaring a variable, and then we specify that function name. So here I am declaring a thread variable, and I am telling it which function to call. So a thread will be created, it will start executing, and it will execute this particular function. Okay. So while it is happening, I also need to either join or detach. So I can do t.join or t.detach. There is little bit of difference between these. Thread join versus detach. For join, we wait for the thread to complete. The code calling dot join is blocked until the thread being joined on completes. Detach. We signal that we do not to wait for the thread, and the thread gets detached from master thread. So master thread is the primary thread that is executing your code, as in this is where your main function starts, that is your master thread, and then you can create other threads as needed. Okay, so we do this, we run it, and it says this is fun. Okay, now suppose I want to create multiple threads. So let us have a vector, and I want to have a vector of threads. So what I can do here, we can declare a vector. Threads, and then I can create for int I equal to 0, I less than 5, plus I. Okay, threads dot pushback std thread, and we call this function. Okay. And then for all of them, I want to join. So for auto threads, oh, I want to thread dot join. Okay. What I can do here, I can comment this out, not needed anymore. Okay, so time to have multiple threads. Okay, now here I created 5 threads, and my function is getting called 5 times. Pretty much expected. But now we have a problem. The problem is many times if you are using the thread, especially for performance gains. Maybe you are running on a system which has 24 cores or 12 cores or 4 or 8 cores, whatever, okay? And you are doing some sort of data processing. So you think that, hey, instead of doing everything in one thread and wasting a lot of time, how about I split the data in multiple parts, say 4 parts or 10 parts, 16 parts, whatever. And then you want to create one thread to deal with one particular part, okay? And if you are doing that, you also probably want to know where exactly you want to start and end. For example, you have some sort of array or vector, okay, and there are multiple threads. So you may want to either create multiple smaller vectors and each thread gets its own copy of data to work upon. That is fine. But if your data is large, because you are seeking that performance optimization, chances are pretty good you do not want to create duplicate copies of that data. So in that case, you may want to know uh, your specific thread, whether you are in thread A or thread B, or for some reason you want to basically identify the individual threads from one another. So for that, what we can do, we can do something called we can use something called thread ID, and it is basically like this, and std this thread get ID. Okay, so let us build. Okay, now you see that there are 5 threads and all of them have unique thread ID. So at runtime, I can keep track of these thread IDs and figure out some way to split data based on this thread ID, and then we can track which thread is working on which particular chunk of data. So this is how we can identify these individual threads. Okay, now one can ask that, okay, if I have this function only for this to run as a thread, why do I have a function here? I can probably use a lambda, and that is absolutely fine. We can have a lambda here. So instead of doing this function thing, what we can do, we can have something like this. So instead of doing this, I can have threads dot pushback std thread. Okay, so I create this, and then I need to specify the lambda here. Okay, I want to capture nothing, no parameters, and then I want some stuff to happen here. And then I say basically this thing here, I copy paste it, and this should work as usual. Okay, so instead of specifying the function, we can also specify the lambda. And just like previous case, it is, you can see the syntax. We already covered this, okay? So this is yet another stuff. Now we want to share some data across threads, okay? And for that, let us create some sort of shared data across threads. So for that, we can create a structure. Okay, and this is basically a small variable where we want to keep track of some stuff. And what we are doing, we are simply incrementing it here. Nothing too fancy. Okay, so in main function now, what I want to do here, okay, so instead of doing this, okay, so threads dot push back std thread. Okay, so we have here, and then I want this counter. Okay, counter I need somewhere inside this. So for that I need to declare that counter variable, counter, counter, and then I want this variable inside this one. Okay, so I want that counter variable accessible inside here. And then from this thread, I can specify, I can counter dot increment. Okay, so we have 5 threads here. We join for them, and then we can print the counter value. Okay, time to build. Oh, and then run it again. Okay, wait. We need to run this a lot more times to see some fun. Let us run this and I equal to 0, I less than 1000, plus I, and this one. So we start it from 0, and we expect 1000 here, or okay, 5 threads are here, so total 5000 times. Let us see what comes up. Okay, okay, we have a problem. Now, if you see here, we have total 5 threads. Each thread increments it 1000 times. So total 5000 times it should be incremented. We started from 0, but the counter is stuck at 4154. What happens if I run this multiple times? Okay, now it is 3082. Now it is perfect 5000, and it is perfect 5000 now. So wait, what happened? We can run it again here, and it is coming to 5000 now. But it was kind of wacky. So what is happening here, that there are multiple threads and they are trying to modify same variable in parallel. Okay, and that is a big no-no, because then there is no guarantee what will happen to the data. We can get 3000, we can get 1000, we can get 4000, we can also get correct output of exact 5000. Basically, it becomes wacky. Okay, so when we are sharing the data sharing between threads. Okay, parallel reads are absolutely fine. Okay, so there may be 100 different threads. All of them may be reading from same variable, and it is absolutely fine. There is nothing wrong with that. Parallel writes are uh, absolutely not fine, which means that whenever you are trying to write something, you can't have parallel writes happening at same time. Okay, you have to sequence them, or at least at one time only one thread should be able to write in the variable, and while the write is happening, nothing can be read. Okay, uh, reading data while something is writing into it is absolutely not fine. Okay, so whenever a write is happening, only write can happen and only one write can happen at a time. For reads alone, you can have crap ton of parallel reads happening at same time. Nothing will change. So basically, whenever you are going to update the data, you have to be a little bit careful. Okay. Now, what we want it to basically somehow sequence it. Okay, we don't want multiple threads to be able to write at same time. Solution, it is called mutex. Okay, and it is the same mutex that you studied in your operating system course. Okay, so what we do, we declare a mutex, lock it before write, write, unlock it uh, after write. Okay, so what we can do, we can include mutex, and then here we can declare a mutex. Std mutex -m, and then here in increment I can do underscore m dot lock. So I will lock the mutex, write the value, and then I will unlock. Okay, so let us build it again. Run it. Okay, now no matter how many times I run it, it is never going to be wacky ever again. Okay, there is absolutely no chance in holy hell that it can provide some output which is not 5,000 for this particular case. Okay, because I have basically put a mutex locking and unlocking. So the idea is that whenever we involve a mutex, only one thread at a time is able to lock it. Okay, so one thread will get the lock, all others will keep waiting here to acquire the lock, and some other thread can get the lock only after the lock here that is acquired here, it gets released here. Okay, now which thread will get the lock in which particular order, that is pretty much random. Okay, but in either case, only one thread will have access to it for writing at a time, and by using this we basically remove that data erase, data corruption, and all that stuff right out of the window. Now, if you remember your operating system class in your college, while talking about mutex and possibly semaphores, so semaphores are just similar to mutex, except you have a counter with that, so you can have multiple locks at same time. Uh, you have something called critical section, okay, and whole discussion of that mutex and semaphore happens around somehow protecting that critical section, that this critical section should not really go haywire. Okay, so this right here, this is your critical section, this is your critical section. Okay, this is the stuff that you want to protect. So this will be your critical section for this particular case. So whenever you are dealing with threads, whenever you are sharing the data, you will have to figure out which data to be shared. Okay, you have to club it together, the update operations, wrap this between lock and unlock, and that part will be basically your critical section. So if someone ever asks you that, hey, do you know how to find the critical section? Now you know how to find critical section, okay? And if you are ever debugging something like data arrays, data corruption, where multiple threads are there, you only have to find that critical section that is not guarded with a mutex, okay? And in that case, again, critical section will be something that is being shared between threads, and threads are in a position to modify it, okay? Any questions so far? Okay, I think there are a couple of questions. Are there any alternative compilers of Python that don't implement global interpreter? No idea. When we create threads in C++, are we creating P threads or are creating green threads? Can you please do a small explanation of P threads? Okay, so C++ does not really have any concept of green threads. Okay, so whenever you are going to create a thread in C++, it is going to create a thread by involving some sort of syscall native to that particular platform you are targeting. So, for example, for Unix-like systems, that will be a clone syscall basically. Okay. On Windows, there will be some other API. I have no idea, but the point is that you will be creating the platform threads, okay? Because C++ as a language has no concept of green threads, and the basic difference is that a green thread is something that gets implemented uh, almost entirely within that language's own standard library, entirely within user space, and from the kernel, it looks like one huge thread, just that you are basically uh, uh, trying to simulate bunch of smaller threads on top of one platform thread. So just like your single core CPU is basically switches between tasks after some sort of some time quantum, you implement some strategy like that, and you basically end up avoiding the overhead of creating threads for cases where you don't really need uh, we don't really have a very pressing need to go for platform threads. So, for example, if you are looking for optimization or the performance improvement, okay, and your stuff that you are, whatever stuff that you are trying to do, it is something that is basically kind of resource bound, that you want it to run on multiple cores at same time. So at that stage, green threads won't really be that useful. Okay, you will need platform threads. But if your stuff is something like where you are spending a lot of time waiting, okay, and you are doing the threading part only to reduce the overall waiting time. So instead of waiting in sequence one after another, you basically try to wait in parallel. In those cases, your green threads will be way better than platform threads. But then again, C++ doesn't really have any concept of a green thread. Okay, now there is one little bit of problem here, and the problem is what happens if you acquire the lock and for some reason you forget to unlock. Just build and see what happens. Okay, to terminal I go. Okay, and now this code is stuck because first thread got the lock, then function gets over, and now no other thread can get the lock because this lock is not released here. Okay, so our code is basically in a deadlock type of situation. Threads are waiting for a lock to be available, except that the lock cannot really be unlocked ever again. Okay, So this is a common mistake actually. So what we can do here, instead of doing this unlocking part manually, what we can do, we can automate this. So by automate this, what I mean, we can have something called lock guard. So we can have std lock guard, std mutex lock. Uh, okay, I have to specify the mutex. Wait, what? Lock underscore m. Okay, now I build this again. Okay, build is finished. And now that deadlock part is gone again, even though uh, I am not doing anything explicit with this particular lock object here. So what exactly is happening? I created that lock object. Somewhere in the constructor, this mutex gets locked. And as soon as this particular variable goes out of scope, a destructor is called, and somewhere in that destructor, our mutex is getting unlocked. So even though we are not releasing it, we are not acquiring and releasing the locks specifically, basically explicitly, it is still happening. And just by removing the chance of error where we acquire the lock manually, but we forget to release it for some reason, we just eliminated that footgun entirely. Okay. So as soon as this goes out of scope, this basically unlocks the lock part. Okay. So what we did here, okay, so mutex, there are two options. Manual, we create mutex, we lock it, then we do something, then we unlock it. Okay. Second one is this lock guard. So std lock guard mutex type, and then we have this. Okay. Locking happens automatically at construction time. Unlocking happens automatically at destruction time. Okay. Then we also covered about deadlock. First case is thread A acquires lock, forgets to release it. Now thread B cannot get unlock at all. Okay. Second option is, okay, wait, is screen share disabled now? Okay, second option is thread A acquires lock A and threads acquire multiple locks, but in different order. What that means? So there is thread A, there is thread B. It locks mutex M1. Okay, this locks mutex M2, and now it wants to lock mutex M2 here, and it tries to lock mutex M1 here, except neither thread A nor B can proceed. Why? Because in both cases, the locking order is different. So M1 is locked here. If the locking order was same, thread B would have been stopped here. Okay. And thread A will get that second lock, and then it will proceed, and then hopefully it will unlock both mutexes. But that can't happen either because it also needs a lock on mutex M2, but that M2 has been locked by thread B, which is waiting for lock on M1. And now both are basically stuck. Thread A is waiting for M2 to be available, B is waiting for M1 to be available, and both are the threads are doing absolutely nothing. So none of the mutexes are going to be unlocked. So basically, we are stuck here perpetually. Okay, so what we do? Solutions either have one mutex or use use exact same order for locking, unlocking in all threads. Okay, and unlock. Okay, you can do it in any order, by the way, so it doesn't really matter. So as long as you do this, you will basically avoid most of the deadlocks in your code. Okay, so basically this is the basics of thread. There are other topics as well, as in there are specific semaphores where you can have uh, multiple locks up to certain counter, or you can have some sort of time blocking where you want to either get a lock or basically hit the timeout, and based on timeout you want to possibly do something, for example in this case of deadlock, or maybe you are waiting for a lock that rarely gets released for some reason, so you want to have some sort of threshold there, so you can do something else instead of getting stuck perpetually. So those are the cases there. Then there are some other use cases like futures and promises, but those are not something that you will be using very frequently unless you are someone who writes C++ day in, day out as a professional C++ developer, which most of us are not actually. So we will not go into those topics. So with this, that C++ series basically comes to an end. And for Maldev, we will be mostly using only these parts here. There will be some little bit extensions here and there, but those will be covered later as and when required. So now I can take questions from you related to basically any topic you want, either this lecture or any previous lecture. So anyone got any questions?